Hi, in this video we are going to talk about backtracking algorithms. Let's understand backtracking with an example. We are given a string, we need to generate all permutations of this string which do not contain AB as a substring. So if we take ABC as an example, there are 6 possible permutations of this string. Out of these 6 permutations, these 4 permutations do not have AB as a substring. There are 2 permutations, ABC and CAB. These 2 permutations have AB as a substring. So we do not print those permutations and we print rest of the 4 permutations. So how do we write algorithm or program to solve this problem? The first idea that comes to our mind is, we know the standard algorithm for generating all permutations. We use this to print all possible permutations, and then before printing any permutation, we check whether this permutation contains AB as a substring or not, right? Let us talk about the naive solution first, then we'll see how backtracking optimizes it. So we first generate all possible permutations. I have not written the logic to filter only those permutations which do not contain AB as a substring. So this is where we print all the permutations. So I can add a condition here, print it only if AB is not a substring of it. So in C++, I'll write something like str.find AB if this is equals to npos. Npos is a variable in string class, is a constant in string class, which indicates not found in the string, right? The substring not found in str. So if that is the case, then only print it, right? So I'll put this in the if condition. Now this program prints all permutations which do not have AB as a substring. So what I did, I took the standard permutation generation program and then I added this condition. So what does this program do? This actually generates every permutation. And how does it generate permutation? It begins with L equals to 0. It puts every character after L at position L. So it first puts A, then it puts B, then it puts C. So when it puts A, it actually fixes A at its correct position and recursively calls for remaining string. This is where it makes recursive call for remaining string after fixing the current character at current position, and passes L as L plus 1. So L, your A is fixed and A is recursively called for L plus 1. So at this position, you now fix 2 remaining characters B and C, right? And then you recursively call for L equals to 2. So when you call for L equals to 2, L becomes equal to R. So you print this string. So A, B are there, and then C will come at C is the only character left. So it's there at the last position. So you print this string. Here B is only last character, so you print this string. So we are incrementing L. Now why are we doing the swap operation? Why are we swapping the last character, the original character back to its original position? The reason for this is simple. Once the recursive calls of this are over, you want A to be back at its correct position. So you initially swapped A with A. So initially your string was A, you run a loop for I equals to L. So you made ABC, then recursively called for this. Now you swap B with A, so you get BAC. So before you move on to the next recursive call after B's call, you want this string again to be ABC, right? That is why you do a swap, and this is done recursively to regain the original string so that we can put remaining characters at position L and then recursively call. So this is how a string permutation function works. Now we've talked about a solution, a naive solution, which modifies this string permutation function to print only those permutations which do not have AB as a substring. So in backtracking solution, we don't just generate all permutations then check. We cut down the recursion at this moment only whenever we feel like that AB is going to be formed in our string. So what we do is we put some condition before making the recursive call, right? And this condition ensures that you don't make a recursive call if AB has occurred in the string, right? So at this point, when your B comes after A, you stop the recursion here, right? It doesn't look like a big optimization for this string, but imagine a string which contains hundreds of characters beginning with AB, right? So you will ignore all the recursive calls if you're cutting down the recursion at this point only. So that's the idea of backtracking. So in the previous solution, in the naive solution, We were generating all permutations and then we were checking which of these permutations are valid. Here we are actually cutting down the recursive calls, right? And we are making sure that we don't go down if this current set of solutions, the current steps do not produce any of the valid permutations, right? So that's what we do in recursion. So how do we modify this code? We just need to put some condition here so that this function is called on this part is called only when this move is a valid move. So what we do in backtracking solution is we add a function isSafe so that we don't proceed further in recursive calls if this particular permutation is never going to lead, the current set of solution is never going to lead a valid permutation. So we put a condition here in this, put this part in a condition, if isSafe strlir, then only make these three steps, right? Otherwise don't. Now how do we write isSafe function? We want to ensure that AB doesn't appear as a substring, right? This step doesn't cause AB as a substring. So what I've done here is I have checked for the previous character. If the character at L minus 1 is A and the current character with which I'm going to swap, right, is B, then there's no point of doing this swap, right? Because it won't lead to any valid permutations. I return false. So since I have L minus 1, I've checked for this condition that L should not be 0, right? So this handles pretty much almost all the cases, right? This is, this ABC is cut down, this recursive call is cut down by this, right? But it does not handle only one case when your string is CBA here. So here your string was CBA. You first swap B with B, you get CBA as an output in this recursive call. Then when you swap B with A, right? So this string becomes CAB. And this condition is not checked by this part because L minus 1 is C and your current character that with which you are going to swap is A. So you go inside if and you actually do a swap and CAB when it comes, so you don't check any condition here, you print CAB, which is not a valid string. So to check for this particular case, I have added this condition. That this condition is there to handle the cases when your string is something like BA at the end, right? And B and A are swapped and you get AB at the end, right? So you don't want AB at the end. That is why we add this condition. So we've talked about a backtracking based solution for the original problem, which was AB should not be a substring in any of the permutations, and we wanted to print all such permutations. So what is the advantage you get? You must have realized it in the naive solution. We were generating all permutations and then we were generating factorial n permutations, right? And then for every permutation, we were checking whether this is a valid or not. We were doing this much work, right? Here we definitely do less than this work. The actual work depends how your input string is. For example, if the string is BCD, then you will again do this much work because your output is going to be all 6 possible permutations. But if your input string contains many ABs, right, then you will cut down many recursive calls and you are going to do much less work than factorial n in this backtracking solution. Because in backtracking, what you're doing, you're not proceeding further if your current solution does not lead to a valid permutation. So whenever you see a problem where you have a solution and the solution that you have is it generates all possible permutations or combinations and then check whichever of these is valid, right? So if you have a solution like this, you can always optimize the solution by using backtracking. What you do is you cut down some recursive calls by putting an isSafe function before proceeding further in the recursive calls. For example, if you see n-queen problem. So n-queen problem is you are given a chessboard, right? N cross n chessboard, and you want to place n queens on this chessboard such that they do not attack each other. So you basically want to generate all possible permutations of these queens and then you want to see which one of them is not attacking each other. So you just return one of such permutations. So you can again write a solution like the naive solution which generates all possible permutations and then check which one of them is valid. A better solution, a backtracking solution would be while generating the permutations, you add a function isSafe. So whenever you see that two queens are attacking each other, you stop. You don't proceed in that recursion, right? So, and there are more problems like Hamiltonian cycle problems, Sudoku problems. So all of these backtracking implementations, if you look at Geeks for Geeks articles, most of them are having a solution like this, then having an isSafe function before proceeding in the recursive calls. And isSafe function checks whether this current configuration is going to produce any valid output or not, right? So we talked about backtracking in this lecture. I recommend you to solve the practice problems yourself and have fun with them.